Hi folks, so this is our first division rule. I just summarized the properties that we talked about previously, and I am going to discuss this new rule, division rule, and see which one of those properties are satisfied. Well, this division rule is pretty intuitive, and in fact probably the very first rule that would come to your mind is that, well, why don't we divide the surplus in proportion to the agent's claims? So if, for example, you and I claim exactly the same thing, well then, and if there's only two players, agents, well then we should just split the surplus equally then. If my claim is 3 times more than your claim, well, why don't we surplus or award each agent's, my award should be 3 times more than your award. All right, so that's the idea of proportionality or proportional rule. So here's formally how we define it. For any claims problem, CE, well, the proportional rule, because it's proportional rule, I'm not going to use the letter R for this specific rule. I'm going to use P. So the proportional rule for any claims problem CE basically tells us lambda times E, all right? Well, what is PICE is equal to lambda times E? Lambda times C, I'm sorry. That's my mistake. So lambda times CI, where lambda is defined by the following ratio, E, the total surplus divided by the total claim. So remember, this is a claims problem, so the sum of the claims will always be equal to or exceeding E, so therefore this number is less than or equal to 1, but obviously E is positive, the summation of claims is positive, so therefore this problem is always greater than or equal to 0. So that means we are using the same ratio for each agent, lambda, and what we do, we just sort of proportionately give each agent's claim, but again proportionately, and we use the same ratio. Well, let's give a numerical example. So let's suppose the award or the surplus we would like to distribute is 200, and then the claim vector is equal to 100, 200, and then another 100. So there are 3 agents. Well, then, what does that mean? That means the lambda is going to be 200 divided by the total claim, which is 300 plus, this is 200, I'm sorry. So 300 plus 100, 400. So basically 1/2. So what does that mean? That means proportional rule says just distribute each agent proportionately, or meaning give half of his claim. So therefore P of CE is equal to half of the claim vector, which means 50, 200 divided by 200, 100 divided by 2, another 50. So therefore this is what the proportional rule is going to award the agents. Okay? So the question is, does this rule, proportional rule, satisfy those properties? Let's think about it. Well, first thing first, feasibility. Well, feasibility and efficiency. If a rule is efficient, clearly it is feasible, right? Give yourself a moment and convince yourself that that is true. If you're not 100% clear, do not move to the next statement. But again, pause here and think about this. So if a rule satisfies efficiency, it definitely satisfies feasibility. And so I'm going to skip feasibility. I'm just going to look at the efficiency. Does it satisfy efficiency? Well, in this specific example, what does that mean? That means when you sum up the rewards, 50 plus 100, 150, plus 50, 200, which is equal to the surplus. So it basically satisfies this for this specific problem. But is this a proof that this rule is satisfying efficiency? No, it is not. How can I possibly prove that claim? Well, you can't give a numerical example because this has to be true for any claim problem CE. Maybe there is some claim problems CE which where this is not going to hold. So I have to show that this will never hold, or this may sometimes hold, sometimes fail, or maybe it will always hold. So for that reason, I cannot give some numerical examples. So how can I prove that it satisfies efficiency? Well, simple. Remember, it says summation pi CE I from 1 to n has to be equal to E, question mark. So I'm going to do a direct proof. Well, why? Because it's very straightforward. Well, what is pi? Well, remember pi is lambda times ci. So this summation I from 1 to n, pi ce, is in fact nothing but, this is lambda times ci, is equal to this, I from 1 to n, lambda times ci. All right, well, lambda is a constant number, remember? So I can take lambda out of outside of this summation. So it's lambda times summation I from 1 to n ci. Okay, so whatever, but this is just some number. Lambda is also a number, like 1/2 in my previous example. But now let's open this lambda. What is this lambda? Remember, by definition, lambda is equal to E divided by summation I from 1 to n ci. Well, this sum and this sum are identical. And we know the sum... Oh, well, one good question. Is it possible that summation I from 1 to n ci is equal to 0 for some... what is it? For some claims problem. Well, although I did not specifically say we will ignore those cases, but those cases do not really make an interesting statement because, in those claims problem, nobody claims anything. And if E is a positive number, well, first off, this is not a claim. So we have to have E equals 0. Well, E0, claims are 0. Well, this is not really a problem. You see what I mean? So therefore, I can fairly assume that this summation is non-zero. So I can cancel them out. So what does that mean? That I should have written this here, right? I from 1 to n ci. So therefore, I cancel out this sum and this sum. So that's equal to E. So the summation I from 1 to n pi is in fact equal to E, regardless of the value of C and E. You see what I mean? So therefore, the proportional rule is efficient. Okay. Next, non-negativity. Well, can I say that for each agent, what he or she his award is going to be non-negative? Well, yes, Ci is a non-negative number by definition. Lambda is a number between 0 and 1. So there's no way this can be negative. So therefore, it satisfies non-negativity. As simple as this. What about claims boundedness? Well, lambda is a number between 0 and 1. And so it's lambda times Ci. So therefore, this is clearly less than or equal to Ci for any I. So again, it satisfies claims boundedness. So it's very straightforward proofs. Well, what about respect of minimal rights, equal treatment of equals, claims monotonicity, and resource monotonicity? Well, I can argue that it is definitely equal treatments of equal. How do I know that? Well, remember, lambda is equal for everyone. So if Ci is equal to Cj, obviously their rewards will be the same by definition. That's it. Very good. What else? Well, respect of minimal rights is maybe a little bit more complicated. So let's prove that. And I am going to leave the other two as an exercise. Okay? So, how do I prove that proportional rule satisfies respect of minimal rights? Well, what is the definition of respect of minimal rights? Well, it basically says PI, I'm not using RI, remember, because I have now a specific name for this rule. So I change it as P. So the proportional rule is lambda CI, but it should be greater than or equal to, is it? I don't know. Max E minus summation j is not equal to I Cj, comma 0. If you want to prove inequality, well, direct proof is normally is more difficult. So I would prove this by contradiction. What does that mean? That means suppose for a contradiction that proportional rule does not satisfy respect of minimal rights, which means there exists some claims problem such that the PICE, which is this one by definition of proportional rule, doesn't satisfy this inequality, which means it's strictly less than this. Okay, good. Well, what is this term? All right, well, here we go. Well, okay, well, this term, I can't really open this up because E is just a real number. I can't really do anything about this. Very good, all right. What can I do? Well, I can do the following. I can open up lambda, remember? So lambda is equal to E divided by what? Summation I from 1 to n Ci, all right? Times Ci, which is less than max E minus summation j not equal to I Cj, comma 0. Okay, good. Well, I have to get rid of this, this max operator. How can I do that? Well, remember this is true for every player I, right? This is the definition of respect of minimal rights. So if this is true for all of them, but what I can say, what I know is that I need to get rid of this max operator. And I can. How can I? Well, look, I mean, the max operator says the right-hand side of this inequality is either equal to this term or this term. Well, this term, this right-hand side is equal to this, the first term, if the first term is positive, right? If it is negative, well, then it's going to be the second term, which is 0. Well, can it be 0? Well, if it is 0, that's a contradiction, all right? Or is it? Well, it is a contradiction because remember, Ci is a non-negative number, at most 0, at least 0, I'm sorry. This is a non-negative number. E is a non-negative number. So this term, there's no way can be strictly less than 0. So therefore, if this term is 0, I already reached a contradiction. Check. Very good. Because remember, I assumed this for a contradiction and I reached a contradiction. So I'm done. If this term is 0, I'm not writing it. So therefore, assume that this term is equal to E minus summation j not equal to I Cj. Okay? And now try to show that this is also going to lead to a contradiction. And hence, I can conclude that whatever the value of this max term, I have a contradiction, so I'm done. Okay, so E divided by summation I from 1 to n Ci times Ci. Okay, good. Well, here I have too much summation terms and they're not even the same because this summation is missing Ci, right? It's not including I. So what I'm going to do, I would like to make this similar to this. How can I do that? Well, subtract Ci from this side. Well, if you do that, in order not to change the inequality, you should also subtract Ci here. Okay, so this new term becomes what? E minus summation I from 1 to n Ci, right? Because I am subtracting C1, C2, C3 all the way up to Cn except Ci. I also subtract Ci, so now I completed the entire summation. So this is less than or equal to E divided by summation I from 1 to n Ci times Ci minus Ci. Okay, now let's use some notation simplifier. Let me clear this part because I need some space and I cannot erase the other part. So here, instead of calling this summation again and again, I'm going to call this A. All right, I know that it's a non-negative number. In fact, it's positive. So it means I have E divided by A, Ci minus Ci, less than, strictly less than. I don't know why I keep putting this equality. I shouldn't be doing that. So strictly less than E minus A. Okay, well, what can I do? Well, I multiply both sides by A, all right? So that I get rid of this A on the numerator. Well, then what do I have? Well, that means if I multiply both sides by A, I'm going to have E Ci minus A Ci less than E times A minus A squared. Okay? Okay, well, it is what it is. Next. Well, I don't know if it is going to help because I can't see 5 steps ahead, but I can pull all the terms starting with E on one side, all the other terms on the other side. So I have, therefore, E parenthesis Ci minus A less than, strictly less than, A parentheses Ci minus A. Right? Yes. I have Ci minus A. Very good. So I can cancel them out. But you should be very careful when you cancel out terms, because if they're negative, that's going to change the sign of the inequality. Is it negative or positive? So I have to decide that. Ci is the claim of player I, and A is the total sum. I mean, this is summation I from 1 to n Ci is equal to A. So obviously, this guy, A, is greater than Ci, or maybe equal, okay? So therefore, well, can it be equal? All right, very good question. Well, it can be equal, because if it is equal, so this is 0, 0, so 0 is less than 0, contradiction, all right? So therefore, suppose it is not equal, okay? Because again, reaching contradiction ends my proof. So I need to look at, I need to continue looking at cases where I don't reach a contradiction, all right? So therefore, I continue looking at case where A is strictly greater than Ci, but I know A cannot be less than, strictly less than Ci, at least. So A is strictly greater than Ci means this is negative. So I can cancel this out, but it's going to make this term strictly greater than. So what does that mean? That means E strictly greater than A. What was A? A was this sum, I from 1 to n Ci. Well, is this true? Hell no. Why? Well, remember, CE was a claims problem, which means the total claim exceeds or maybe equal to, but no less than the surplus, AE. So therefore, this is a contradiction and there's no way I can continue to the proof because that's the end statement. All right? So therefore, as you see, whatever case I look at, remember I look at the max equal to 0 contradiction, max equal to E minus summation, J not equal to I, Cj. If this is the case, well, then I came up to this parameter. If it is greater than or equal to, if it is equal to Ci, contradiction. If it is strictly greater than Ci, I lead to this, which is not true because this is a claims problem. So whatever you do, there's no way you can escape from contradiction. Well, what do I contradict with? Remember, for contradiction, I assumed that the proportional rule does not satisfy minimal respect of minimal rights. So therefore, it does satisfy respect of minimal rights. Okay? Once again, I leave the others, claims monotonicity and resource monotonicity, as an exercise. Okay?